factors that affect enzyme activity. pH. For enzymes within our own bodies, a pH between 6 and 8 is about what they're accustomed to. So you notice that we hover right around that neutral idea of 7 for our pH. The exception would be those that are found like in digestive tracts, pepsin being one example. It functions best in a pH of 2. So if the pH is very, very low, that means that the conditions are very acidic. And if it's very acidic, we have a lot of H plus ions hanging out in solution, ready to go to work, ready to bond with things and tear things apart, or bond with other things to pull them away from what they're already with. And so this extra H plus actually activates pepsin's active site so it can actually do its job. If you take pepsin outside of that environment, if you put it in a neutral solution or a basic solution, you'll denature it. It will no longer be able to work. It will no longer be active because it doesn't have the components that it needs. It does not have that acidic environment to help it be active and function. Albumin in the white of egg whites, right? If we cook the egg, we denature it. And when we do denature it, it goes from being a rather translucent or transparent egg white to being that translucent. So why do we heat things up? Why do we cook foods? A lot of the reason is to denature the proteins that make it up. Because our body can actually go to work and use less energy to break them down into smaller bits if we've already put some energy into it to denature them in the first place. And that's true for many of the foods that we end up cooking. It's just one of those evolutionary advantages that we are able to do. Not everything can cook its food before it eats it, but since we can take advantage of all the nutrients that are in the food. In some cases, I would have to agree. In some cases, when you cook the food, you actually lower its nutritional content because of what we do to break things down. But by and large, cooking food is typically a help than a hurt. All right, so salinity or salt concentration. This one we might have to think a little bit about why it would affect the enzyme. We said that enzymes are a special class of proteins. What do we use to build proteins? What's the monomer for proteins? Not nucleotides, that's nucleic acids. Amino acids. Yeah. All right, so those amino acids, what makes each of the 20 different amino acids different? The R groups. Okay, so those R groups we mentioned, we didn't have to memorize any of the R groups. We had to memorize all the 20 different amino acids. But I did ask you to consider that each of these R groups give each of these amino acids different properties. Like some are neutral. Some have a positive charge. Some have a negative charge. Yep. Some are water-loving and some are water-fearing. Right. So let's say that you have some of those R groups out there that have positive and negative charges, and they make up like some of this enzyme, because an enzyme is a special protein. You throw in the mix a bunch of positive and negatively charged things. How might that affect the enzyme? In what ways might that affect the enzyme? Why?
Because the positive and negative charges are going to react with each other and make it bend around us.
Yeah, I mean, remember when we first make that polypeptide chain, yeah, you're right. The R groups are going to then start to interact with one another and their environment. Either folding in towards one another, if they're positive, negative. If they're all hydrophilic, then they want to hang out with one another. If they're hydrophobic, they want to hang out with each other and stay away from watery-loving things. And if you throw positive and negative charges in there with everything else, it's going to affect how they fold up. It's going to change the structure of that enzyme. And ultimately, if we change the structure of the enzymes, we're going to ruin that active site. So absolutely true. Another person suggested a couple periods ago that maybe the active site itself has some positive or negative charges, like regions that help pull the substrate in there. And you're right. I mean, there could be positive and negative charges in the active site. That if these higher concentrations of positive and negative charged things find their way into that site and hang out there, they could also change how it's shaped and affect whether it works or not. So that's really what we're looking at with salinity or salt concentration. Joe, you can't just be locked into sodium chloride, although that's the easiest example of a salt that dissolves in water. But really anything that's ionic that dissolves in water could be considered to be a salt. But we use a common example because it's easy for us to remember. All right, another thing that can affect activity would be cofactors. All right, now this can be a little tricky, but we'll keep it simple. Right? If we're talking about simply a cofactor, right, we're going to be talking about an inorganic chemical compound. Right? The key thing there is it's inorganic, so it's not based on carbon. Right? So an inorganic chemical compound that helps activate an enzyme when it's bound to it. Examples of cofactors could be simple ionic metals like zinc, iron, copper, potassium, other types of inorganic metals that have a charge on them. All right, and those would be called cofactors if they help an enzyme become active. Right. The other side of the coin, or the other, I guess, type of cofactor, are coenzymes. Now, here's how you keep them distinguished one from the other. Right. A simple cofactor is inorganic. Right. A coenzyme is an organic molecule, so it is based on carbon, or it has a carbon backbone to it, and they are not proteins. Right? So I mean, if they were proteins, then they'd probably be enzymes anyway. But these coenzymes are organic molecules that are not proteins, but help again get things and move things into the active site for enzymes. These coenzymes can carry chemicals into and help move them into proper positions in the active site. Sometimes these coenzymes will actually nest into the active site to kind of complete the shape, and that activates the enzyme and also helps get the substrate in there, right? It just depends on, again, what is needed by the main enzyme that's going to be doing most of the work. Right? A good example of a coenzyme would be vitamins. Right? Vitamins help weaken the bonds of substrates. That way they can fit in and bind into the active site properly. There are around 13 vitamins that are essential to your existence. If you don't get these 13 vitamins, you no longer function. That means you die. Yeah, it's not good. 13 of them. Some of them you can synthesize. Right? There's a few that you can't, and those that you can't, you tend to find in your diet, right? Just by accident. And then we also fortify a lot of our foods with these vitamins also to try to avoid any type of vitamin deficiencies, like your pastas and your quick box meals, your cereals for sure are artificially loaded with extra vitamins. Enzyme concentration. This is pretty simple. If you put more of them in the same spot, you should be able to have the reaction go quicker. Right? Because you're going to have, if we take the amylates that we have in our saliva and we double the concentration of it in our saliva, that means that we should probably see a doubling of the reaction of breaking down the starches to the simple sugars. Right? And so the reactions will happen more quickly when you have more of them until you start using up substrate. Right? So you have like a crap ton of these enzymes hanging out, just going gangbusters on these substrates that they're working on. And then they start to run out of substrate to work on. Right? Because that's all the enzyme can do is work on the substrate and then break it down to product and then help products be formed, and that's it. So eventually you start to see the reaction slow down because enzymes can't find any more substrate to work on. And then ultimately you'll end up with just a bunch of enzymes hanging out with the product being made. Right? And they're waiting for more substrate so they can go get back to work. So these enzymes are reusable over and over and get used over and over and over and over. A question that was brought up in a class before was asking about do they get used forever? Like, if they can be used over and over and over, do enzymes last forever? And the easy answer is like nothing lasts forever. Everything at some point. Thank you. At some point, things wear out, right? And the enzymes are no exception to that. So if they get wear out from being used, they get worn out from because maybe for a while some conditions that are optimum for them, they're not in optimum conditions, so they denature slightly, so they're not as functional as they once were, they're a little less efficient. That happens again, they get altered some more, and eventually they break, they get ruined, and they no longer function. Which is fine because our body is out there expressing more proteins and building more enzymes all the time. So it's not that we can't replace them, but they're good for hundreds of thousands of reactions before they get worn out or used up. But that's why we still have to emphasize the fact that enzymes do not get used up through most of the chemical processes. To name them, this is something that we could probably mention earlier, but we'll mention it now. If you want to know if the name that you're looking at is a name of an enzyme, just look for ACE on the end, ASE. Right? So like for sucrose, to break down sucrose, we use sucrase. Right? To break down lactose, we use lactase. The ASE on the end will denote that you're talking about an enzyme, and then the substrate that it works on will give you the front end of its name. Right? So those people who are lactose intolerant, right, their bodies do not produce enough lactase to break down the lactose. And so the result is like an achy stomach, and then if you eat something with a lot of lactose in it, you usually get like the runs or
fancy.
you get diarrhea. Because your body can't do anything with it, so it's just gotta pass it along. So there you go. So it's not fun, but that's the way it is.
That's what I like to see.
Well, interesting thing about lactose intolerance is that sometimes you can see it come and go in youth, where growing up, like maybe from birth to like age 5, 6, 7, or 8, they seem to be fine with milk products or lactose products, and then something changes a little bit between ages 8 to 13, 14, 15, and sometimes it'll last all the way through adulthood that they're lactose intolerant. And other times it'll kind of fade away. Their body somehow decides, yes, I'm going to make more lactase now to help take care of lactose when I encounter it. It's really a weird thing, but kind of interesting in the way that sometimes our body decides to fix issues on its own, and in other times it just stays broken. All right, the last thing to mention in section 2.3 here with enzymes is, well, we have all these specialized proteins that help lower activation energy and help reactions to happen. But sometimes we don't want them to happen, right? And these enzymes, that's their job. Their job is to lower activation energy and make chemical reactions happen and happen quickly. So we need to inhibit their activity. We need to be able to stop them or slow them down. And so we're going to close this section of material on looking at inhibitors. Right? By definition, an inhibitor is a chemical that interferes with an enzyme's activity. There are two types. There are competitive and non-competitive inhibitors. Now, I think competitive inhibitors are very easy to understand. Non-competitive inhibitors, we might need to think of as a little bit more. It's not as straightforward as competitive. Right? But we know that there are two things that seem to be very, very important when it comes to an enzyme and its function, right? It's the active site and the overall shape of the enzyme, right? If we mess with either one of those, we've discussed situations where that ruins the protein's ability to function. So that's what these two types of inhibition pathways will do, right? So first, competitive inhibition. Right, a competitive inhibitor is simply going to compete for the active site. It's who can get there first wins. Right, so in this illustration, we have an enzyme with like a little circle for the active site, and then the substrate is shaped like a circle and fits in there, and so normally the reaction happens. The substrate fits in there, and the reaction proceeds. We lower the activation energy, the products are made. If we have a competitive inhibitor in play, then it also has a shape that fits that active site. And it'll get in there and bind, but it's just an inhibitor. It's not the real substrate, so it just sits there. It occupies the space. And so the substrate can't get in there to be worked on, and so therefore the reaction can't happen. Right? So that's competitive inhibition. It's like It's like when you're at like a large like 5K race, 10K race, or half marathon or something, and like you gotta use the porta johns before you have your race. You know, the pre-race poop. You gotta do the pre-race poop, and you go and like the porta potty says occupied. Right? You can't use that porta potty. Someone's already in there. You can't use the enzyme. Somebody's already in there. Right? I mean, you could try, but it'd be kind of weird. And there's always that one that forgets to lock the door, so like it's not quite, it doesn't say occupied, it says open, so you walk up and you're open, right? Right, like what's up with that? And so I'm like, dude, I gotta go, my race starts in 5 minutes, I'm going. You know, but it's like, dude, poop or something. It's like, come on, man.
Taco Bell.
At any rate, though, competitive inhibition is very easy, I think, to understand. Right? If the active site is taken, nothing else can use it. So, inhibitor in there, no reaction can happen. That'll slow things down. Right? A non-competitive inhibitor is a little bit different. Right? We're not going after the active site. We know that the name of the game is the fit and form and function. So, a non-competitive inhibitor will bind to someplace else on the enzyme. And in doing so, it changes its shape and alters the shape of the active site. Right? So in our picture here, we have an enzyme that from before, we have our substrate as before, and if nothing's there, then the reaction proceeds. But if we have an inhibitor, a non-competitive one, and it binds to someplace else on our enzyme, it changes its shape. And now our substrate won't fit. And if it can't fit, then it cannot do its function. Cannot lower the activation energy, cannot make products. Game over, we're done, shut down. Right? This effectively lowers enzyme concentration because if you have a bunch of these guys hanging out, a bunch of amylase again, and we have a non-competitive inhibitor change the shape of some of them, it's like they're not even there. It's like we've lowered the numbers of the amylase enzyme to do anything. Right? We use this, or this is used in like poisons, right? And heavy metal ions like mercury and lead and cadmium, and also insecticides. This is how they work. Right? They're loaded with non-competitive inhibitors that will bind to enzymes that are crucial in some sort of metabolic pathway for the insect or organism, and ultimately shut that pathway down to the point where we either off the organism or whatever. Lead poisoning. This is what lead, when lead gets into your system as a young little kid. This is why we want to avoid exposure to lead, because lead gets in there. It's a non-competitive inhibitor. It ruins neurological pathway construction and builds. So it's kind of interesting, I think, to consider this non-competitive inhibition idea. Now, one last thing to add in here would be another example of non-competitive inhibition that's done in a slightly different way, right? Where the products that we're making actually shut down the pathway, right? And this happens in our cells during cell respiration, right? So at the end product of cell respiration is to make ATP, right? We take a simple sugar like glucose, we add oxygen with it, and then it's like the reverse of photosynthesis. Right? We take that simple sugar, we use oxygen, and then as a result, we produce carbon dioxide, which we don't use, we waste that out, water, and then which we may use for other things or waste it out, and then ATP. ATP is like the Bitcoin of our cells, right? It's like a currency you can use almost anywhere for anything, but it's not as shady as a Bitcoin. This is a little bit more solid of an idea. Okay, so ATP synthesis, if we have too much ATP, we shut this pathway down in one way by feedback inhibition. Feedback inhibition is a type of non-competitive inhibition. And so the diagram tries to explain this a little bit, and we'll walk through where this happens in cell respiration briefly. All right, so we have our initial, if this is cell respiration, this could be like our simple sugar, and at the end we make ATP. Well, if we make too much, then the extra ATP, instead of being used for powering energy things in the cell, it actually floats around, and this ATP molecule actually interacts with enzyme 1 and is a non-competitive inhibitor for it and shuts it down, like inactivates it. So if I shut down enzyme 1, I can't do the rest of my steps here. So it's the feedback. It's I've made too much, and making too much, it lends it to non-competitive inhibition by binding to one of the necessary enzymes and making it inactive. Right? It can no longer make more ATP. It has to wait until ATP is used up or goes to lower amounts before the ATP gets removed from that enzyme and starts back up again. Right? So maybe another example with a little bit more description to the illustration. So we have our start. This would be like our starting, maybe sugar or something, and then we're moving through our pathway here for cell respiration. The first set of steps in cell respiration is glycolysis. Glyco meaning sugar, and lysis meaning cut or break. So we run through glycolysis, and the end product is ATP. Well, if we have a bunch of ATP being made and we don't need any more, the extra ATP will actually bind to one of the first enzymes in this process, known as phosphorfructose kinase, right, or PFK. If we bind to this, the ATP binds to it, it changes the active site. So no longer can our simple sugar connect there and start this chain of events to get us through glycolysis, which effectively shuts down cell respiration, because if you can't move through glycolysis, you can't get the Krebs cycle, you cannot get to finally making ATP. You shut it down. Right? It's a very effective way to control the function and production of a product through some sort of enzymatic reaction. Now, this is just one example of many where we can shut down pathways. There are other spots in our cell respiration pathway that can shut things down, just like this. There are many enzymes that work along the way that pass one product to the next step in the sequence. All right? But it's important that we actually understand that from all of this, that we regulate ATP. We regulate the energy currency of a cell by feedback inhibition, which is a type of non-competitive inhibition that controls the amount of ATP being produced.